We are now recording. We'll go from the current slide. Actually, move over from there. But I did want to remind you again of the announcements. I don't see them here, but you know what they are. Math team looking for good folks, a few good men and women, okay? So if you haven't already considered it, please consider it. They meet Friday at noon on the Birmingham West Campus in the Science Building. That's the C Hall C100. Mr. Rossi is the coach, and from what I understand, they have a really good time and learn a lot of math at the same time. And then, again, they meet on Monday afternoons at 3, same place. And if you want to try to get together here, I don't have many office hours left since I picked up 2 second mini-term courses. And then what's even worse, and it's not affected this class yet, but it might in the future. If you notice, got a little bit of grading done in this, to do in this grade book, and quite a bit to do in that grade book. And here's part of the reason for the backlog. One of these classes I picked up second mini-term is a physical science class with lab. So every Tuesday and every Thursday, pretty much, we have a lab, okay? Which means lots of, and there's about 20 to 25 students in the class, so lots of labs to grade. Those are hard to grade. We have a test fairly frequently too, 5 to 6 tests during the term plus the final, and that's in 8 weeks, so it's almost 1 test a week, and those have to be graded. So that's really swamped me there. Secondly, one of the course I teach this afternoon is a full-term course, but it's the first time I've taught it in several years, different book, different everything. So I'm having to come up with new tests for that one every time we have a test. That's what I was working on in the last class period, was working on that. I know y'all are real sad to hear the song. It's pretty, the violin music is pretty though, isn't it? Yeah. And then the other mini-term class I picked up is a brand new class. Has never been taught before on this campus or on any campus here. They taught it in one other school somewhere in the state. New book, brand new course. I'm having to develop it from scratch as I go. The 098, I'm developing the test as we go, but at least I...
What's the new class?
It's a Physics 112. It's for the sonography program. Those are the students doing, it's called DMS. I don't know what that stands for, but it's sonograms and things like this. So the students have to have a little physics to go with, the medical end of it. So have to come up with a brand new physics class, a book I've never taught from, and the book is not bad, but the PowerPoints stink. They're awful. All they are a few illustrations here and there, no lecture notes or anything like that. And as far as I can tell, I haven't found the test bank yet. And I have to develop a test by this afternoon at 4 o'clock on the other campus. And I've got a class that ends at 3:15 here. So things are not looking good for that class and that test today. So my office hours almost disappeared, and I've got all this stuff to grade and to do and develop and stuff like that. So it's really sad, wasn't it? That's really satisfying.
Did you hear about Stephen Hawkins?
Yes. That was sad too.
Wasn't he a physicist?
Oh yeah. I mean, he was a physicist par excellence. Got a pen here somewhere. This is Tyler, right? Okay. Yeah. The question was about Stephen Hawkins. Does anyone know anything about him? He died, I think, just recently, last day or two.
Didn't he figure out about the multi-universes and all that?
He's involved with a lot. He's the one who probably has developed our best understanding of black holes. They were theorized before, but he's really developed the more information about them than anyone else. He had a very good selling book Brief History of Time, which is an interesting title, and then I think he came up with a simpler one, A Briefer History of Time. He has done a lot on the unified field theorem. They actually made a movie about him in the last few years, The Theory of Everything. That's what the unified field theorem was about. Probably one of the brightest people on the planet until he died just recently. But the other thing that's rather striking about him, okay, I'll say this too. He's appeared on shows, I didn't know this, but I heard it on the radio this morning when I was hearing about his death. He was on The Simpsons, if you can believe it, okay? And they named another couple of things, and one they left off, and I couldn't believe they left it off, Big Bang Theory. He actually was a guest star on The Big Bang Theory, okay? So he's made it on television. They said it, he's kind of like a rock star among physicists, which are not common, Albert Einstein was probably pretty close to one. And then people like, who's the guy that hosted Nova for many years? Carl Sagan was, pretty famous, and Feynman, Richard Feynman, another fairly well-known, well-respected, popular physicist. But the thing that sort of sets goodness now. What's his name again?
Stephen Hawking.
Stephen Hawkins. Goodness, the old gray cells there leaving, I think. Apart from just about everybody else, besides being a brilliant physicist, brilliant physicist. And what killed him was ALS. Has anyone ever heard of it?
Well, my cousin's other granddad died from that.
What's that?
My cousin's other granddad died from that.
Yeah. It's a debilitating disease. If I had to pick one disease I would fear the most, it would be that one. What it does is a neurological disease, and the disease attacks the nerves. And the nerves are the things that control everything, okay? Mostly the motor nerves. So after a while, you can't grasp, you can't hold things, you can't use your hands, you can't use your feet, and ultimately, you can't breathe because those are muscles being controlled by nerves. But Stephen Hawkins, because of his incredible mind, absolutely brilliant guy, he has lived on life support for decades. He's had a machine breathing for him. He couldn't speak. Has no control over that. So he types in messages on his computer, and that is a voice actuated, and the computer reads that. And he's given lectures doing that, He's written books doing that, His TV appearances had to have that's an artificial voice. It wasn't his voice. And unfortunately, in the last few years, I don't know how long, they said it this morning, but just sort of a general thing, I didn't catch how long it was, his health has gotten even worse. He couldn't even use the muscles to do the things to help communicate. So he was going downhill fast. Now, you mentioned you knew someone who had died from it. Does anyone know the common name for the disease? You don't. Lou Gehrig's disease. Okay? Lou Gehrig was an outstanding first baseman for the New York Yankees back in their power heyday. In fact, he was first baseman who played with Babe Ruth, I think. They were just almost unbeatable. They were just incredible. he was called the Iron Man of baseball because he never missed a game, ever, okay? And he was a power hitter, he was a consistent hitter, a great first baseman, but suddenly he started having trouble with the bat and coordination and the ball and stuff, and finally had to miss a game. But he set a record. I don't know if it still stands or if Pete Rose may have exceeded it, but you know, it stood for decades of longest streak of never missing a game. And they diagnosed it to be ALS, which of course meant he was losing all muscle control and everything. And there was a movie made about him. I can't remember what that was called, but he gave a speech that he's the luckiest man in the world, you know, because he got to play the game he loved before the disease took it away from him. Well, until a few years ago, quite a few now, that's all I knew about ALS was a few, and it tended to be sports people. Catfish Hunter, who was a pitcher for the Oakland A's and some other teams, he died of it. There was a coach, I think a high school football coach, somewhere in the area here, because when we moved to Birmingham, I remember seeing them talk about him on the sidelines. He could hardly move, but he continued coaching until he just couldn't do it anymore. And then I went to work at Southern Research Institute. Worked there from 87 till 96 or something like that. And I was working on a project with this really great technician they had there. I mean, he could do anything. Fantastic electrical and stuff like this. And he started complaining about his right arm. He just had no control. He had to start doing things left-handed. I said, have you been checked for arthritis? Because you're describing what my dad, you know. He said, no, I went there to a rheumatologist, and he said there's no indication of that. He sent me to another specialist. Well, another week or two came back. Yeah, it went by, and we were down in the place where we were working on the project, and he said, well, I got the diagnosis. I said, oh, what was it? He said, ALS. And he tried to keep working as long as he could, but he found out he couldn't collect disability because he couldn't do everything. So he had to actually quit the job, and as far as I know, he died. I mean, I didn't keep up with him. But about the same time, this pastor right down the road from where we lived, he was diagnosed with it. And I mentioned that to Don. He said, yeah, he and I got the news on the same day. So there, I'd never known anyone personally, just a few, mostly sports people, that ever had it. And here within a few weeks, I found two people, one that preached at the church right down the road from where we lived, and the other one I worked with at the school at Southern Research. Both came down with ALS. And the pastor died within just a few weeks, maybe a month or so. Died and hung on for a bit longer, I think. And then I came to work here. This was Bethlehem State Technical College at the time. And the librarian here, who used to work at Southern Research Institute as a librarian there, I didn't know her then, but we got to be, because of that connection, or we got to be pretty close. Then her husband was diagnosed with it, and he died from it. And of course, there's no avoiding it because your whole neurological system shuts down. And the sad thing about it, your mind's still there. Those nerves don't get affected by it. It's only the motor nerves. And Diane Gregg, the librarian here, said it was so sad. Her husband, tried to keep doing as long as he could, but when he got so he couldn't do the basic ruddy things for himself and had to have somebody else doing everything for him, she said he just gave up. He quit eating. She thinks he basically didn't want someone else taking care of him, and he didn't know. Stephen Hawkins, that mind of his, they did everything they could, and he lived for decades with it. Of course, he was diagnosed very young, and In fact, another physicist that was on the radio this morning said that he thinks the disease may have actually helped him, in not physically, but mentally, because he learned to think and could do anything else but think. And he said he thought much better than all the rest of us put together. So anyway, yeah, sad thing. I shouldn't have gotten off onto that, but he's one of my heroes. Okay. All right. So that's why you need to join the math team. Okay. I'll work the problems on this one. Any questions before we get going on that? All right, we're on page 170 in chapter 3, section 3.1, example 3, finding the extrema on a closed interval. Okay, so here is your function. Let me get my pen set up. Okay, here's the function. F of x is equal to 2x minus 3x to the 2/3. Yeah. Oh, you don't need a projector, do you? What is this? Huh? Okay. Sorry about that. Okay. Not to. Okay. Okay. On the interval, and this interval is a closed interval from -1 to 3. Okay? Find the extrema on that. Now, what do we mean by extrema? Maximum or minimum. And this is the absolute maximum, absolute minimum. Okay? Not relative, where we will hit those. Oh, my goodness. He's still my heart. I think I recognize this guy. Okay. Jeremy's here. Okay. We're winding up section 3.1. By the way, did everyone here, I'm guessing I know the answer to this, get the second test? Okay, did you get the second test? Okay. All right, let me get that for you before I forget about it. Is that it? No. You wish. I don't know if you realize this, but this book has much more reasonable test bank than what the last book I taught from. It was awful. Okay? This is very straightforward. Okay? Everybody else got it, right? Now, I think I've sent it to the folks who aren't here. The one, Nathan. Hopefully he's gotten it by now. Okay. So find the extrema, the absolute maximum, absolute minimum on this interval. Okay? What do you reckon we do first? Where are the candidates for your extrema, your maximum or minimum? What are the candidates that you would consider? Yes, where the derivative is 0 or does not exist. The endpoints of your, yes, the endpoints of your value. So he mentioned derivative. We need to take a derivative. Good thing to do in this course, right? So what is f prime of x? Not that hard, the first part anyway. 2 minus 2 x to the negative 1/3. Okay. Now, and where are we considering that? Where it's equal to 0 or doesn't exist. So let's start with the 0. Let's set it equal to 0. Now I want to rewrite that slightly. That would be 2 minus 2 over the cube root of x. And that's equal to 0. Do you agree with that? X to the negative 1/3 is 1 over the the cube root of x. Okay? Now, how do we solve that equation? Okay, you're saying add 2 over root 3 over cube root of x to both sides? Is that what I understood? That's a good move. It's legal in most states. So we'll do that. So these go away, and you have, I'm going to rearrange, well, no, I'm going to leave it alone then. We'll have 2 is equal to 2 over the cube root of x. Okay, now what? Say again? Divide what? Divide out the 2s? That sounds like a good move too. We'll divide by 2 here and divide by 2 here. And the 2's go out, and you're left with 1 is equal to 1 over the cube root of x. Is that what you meant? Yes, say yes. Yeah, yeah. Oh, yeah, of course, that's what he meant. Okay, now what? What are we trying to do? Say again? Yeah, we set it equal to 0, so this is finding the 0 of that. But what we do in doing that is solve for x. Now, I find it hard to solve for x in the denominator. So what might you choose to do? How? With the minus sign in it? Well, you see that minus sign means it's in the denominator. That's why I wrote it this way. Hopefully to make it easier to see what to do. What if you had 7 is equal to 3 over x? How would you solve that for x? Multiply by what? The cube root of x. Both sides by the cube root of x. Okay? Now what does that, over here, those disappear. And what we have here is the cube root of x is equal to 1. Right? Now, what could we do to solve that? Trying to isolate the x. How do you undo a cube root? Say again?
This multiplied by cube root. Once you square it?
Not square it.
Cube
Cubit! Yes! A cubit, that's it. Oh, never mind. Okay. Besides the point. We cube both sides. Right? And what does that give us? X equal 1. All right, I feel like a dentist here pulling teeth. Okay. So, we have one place where the derivative of this is 0. Okay? Because, if you think about this, 2 minus 2 over the cube root of 1. The cube root of 1 is 1. So this would be 2 minus 2, 0. Yes! That works. Okay. Now, what's the other condition about the derivatives? Where it doesn't exist. So remember, your derivative here, I've written over it, is 2 minus 2 over the cube root of x. I've crossed it out. So that's the derivative. Where does that not exist? When x is equal to 0, because the cube root of 0 is 0, and you still can't divide by 0. So it doesn't exist at x equals 0. Okay? This is where the first derivative and x equals 0, and both of these are in that interval, right? 0 and 1 are both in there. Okay, this is where f prime does not exist. Okay, that's not a 1, that's a D and E. Okay, does not exist. All right, those are two places we need to consider. What's the other two? The endpoints. Okay, so you can do this any way you want to. Now that derivative, you took that just to find where it's 0 or doesn't exist. We go back to the function to determine the extrema. Okay, I'm running out of room pretty rapidly here, so let me do it up here. F of, where do you want to start? Which one you want to use first? Say again? 3? Okay. F of 3 is equal to what? Yeah, 2 times 3 minus 3 times, get out of there. It's what? It's the cube root of 9. 3 squared. Okay. The cube root of 9. Okay. Okay. I don't know exactly what the cube root of 9 is. Cube root of 8 is 2. And the cube root of 9 would be 2.1 or 2.2, something like that. Okay. So this would be 6 minus 3 to 2, something a little bit more than 2. So this will be a little bit greater than 6. So this is going to be, anyone got a calculator? Make me do all the work here. I don't know what's wrong with this picture. Okay. Chasten's here. Anyone got a calculator? Do 6 minus 3 times the cube root of 9. Hopefully you know how to do the cube root of 9 on the calculator, right? This is example 3 at the top of page 170 in chapter 3, applications for the root of differentiation 3.1, extrema on an interval. It's going to be a slightly negative number, right? Help me out, somebody. These calculators are kind of slow, aren't they? Didn't know they were that slow. You got, huh? Okay, you did 2 times 3, or 6, minus 3 times the cube root of 9. I already figured cube root of 9 is something a little bit greater than 2. 3 times that will be a little bit greater than 6, but it's negative, so it'll be 6 minus something a little bit greater than 6. That's going to be slightly negative. Huh? That sounds right. 2.24? 6.24. Okay. Yeah, okay. Now do 6 minus that. That would be negative 0.24, right? Okay. It's about negative 0.24. Okay? So there's at 3. That's at the right-hand endpoint. What one do you want to do next? Negative 1. So we'll do f of negative 1. This is going to be a little bit easier. 2 times negative 1 minus 3 times the cube root of negative 1 squared. And what's that going to be? Negative 2 minus, now what's negative 1 squared? 1. Cube root of 1 is 1, so it's negative 2 minus 3 times 1. And that is negative 5. Okay? we have a contender for the minimum, and that one could be a contender for the maximum. But we still got these two to try. So which one you want to do next? These are your critical points. Those were your endpoints. Second? 0? Okay, y'all going for the easy one, aren't you? Okay, this would be f of 0 is equal to 2 times 0. I think I can do that one. Use it on your calculator, okay? Minus 3 times the cube root of 0 squared. Hey, I think I can do that one too. What's that? 0. Okay, that's wiped out 3 as an extremum. It's not your smallest. Right now, -5 is smaller than that. And it's not your largest because 0 is larger than -0.4. So that one's out of the picture. Okay? One more to go. And what's that one? F of 1. Okay? And what is f of 1? That's 2 times 1. I think I can probably do that without a calculator. Minus 3 times the cube root of 1 squared. What does that give us? Anyone do it? I don't think you need a calculator. 2 minus, what's 1 squared? Yes, 2 minus 3 is -1. Okay? So, that one's out of the picture too. That's not an extremum. So, 0 is the relative max, it is the absolute max, and -1 is the absolute minimum. Okay? Now, if you look in the book, you see that illustrated pretty nicely. Your minimum is at -1, -5. That's what we found it to be. It went up to 0, 0, and that's the absolute maximum here. It went down at 1 to -1, okay? Not a maximum or a minimum. And then it went up to 6 minus 3 root 9, which would be -0.24, we figured, or something close to that. It's in between -1 and 0, so it's neither a max or a min. Okay? So there you have your minimum at the left endpoint and your maximum at 0. Does that make sense? Okay. Oh, and they got in the book -0.24 for alpha 3 also. Now, example 4 is at larsonCalculus.com for an interactive version of that type of example. Let's do that one. All right, for me to erase this. Okay. So let's do example 4. Find the extrema of f of x is equal to 2 sine x minus cosine 2x. Okay? On the interval, closed interval from 0 to 2 pi. Okay. What are we going to do first? You got several things you can choose from. What do you want to do first? Take a derivative. Sounds like a winner to me. Okay. F prime of x is going to be what? Two cosine x. Did you say plus? Yes, plus 2 sine of 2x. Very good. Okay. Now, what two things have we got to consider? Where that is
0.
equal to 0, or where it's undefined. It does not exist. Well, guess what? Sines and cosine functions are smooth, continuous functions everywhere. So therefore, this has no place where it does not exist, where it's undefined. To get undefined, you have to have 0 in the denominator, square roots of negative numbers, or logs of 0 or negative numbers. That's pretty much it, that we got so far. We may run into some others, but those are pretty much it. Sines and cosines. Oh, tangents, secants, cosecants, cotangents. Oh, they have lots of places they're undefined. So yeah, you would have that. This is sine and cosine, smooth and continuous everywhere. Okay? So, how do we solve that equation there? Ooh, go back to trig class, huh? Anyone remember how to solve an equation like that? Yeah, tough beans, huh? What's the problem here? The cosine is of x, the sine is of 2x. You're not even, okay, you got two different trig functions, that's a problem. And then two different arguments of the trig function. That's an even bigger problem, maybe. So what can we do? Ah, very good. We use a trig identity to see if we can make things a little better on that second front. So this stays 2 cosine x. And then what did you say 2 sine 2x is? Okay, so that'll be plus 4 sine x cosine x. Now, do y'all remember how that came about, or do you even care? You're just looking at the thing in the front, which is fine. After a while, that's what we all do, but if you wanted to go back and review that, we could, but this is okay. Now what? This is looking maybe a little better, because what can we do? Say again? I can't hear what you said. What's the F word? Factor! What can we factor out of here? The rest of you, some of you haven't been in my class before. When I say what's the F word, that means factor, okay? Okay. And now if that offends anybody, I won't say it anymore, but that's what we mean here. So what's the common factor here? Not just that. 2 cosine x, right? What do you have if you factor that out? 1 plus 2 sine x. And that's equal to 0. Now that is something that's doable. Why? Zero product principle. Right? You got two things multiplied together that the product is equal to 0. What does that tell you about either one of those? They've got to be equal to 0. So either 2 cosine x is equal to 0, or 1 plus 2 sine x is equal to 0. Okay, now where in this interval, 0 to 2 pi, is cosine, well, let's see. First thing I'm going to do here is divide by 2. And guess what? Cosine x equals 0. The other way you could do that is either 2 is equal to 0 or cosine x equals 0. 2 is never equal to 0, okay? So then you're left with cosine x equals 0. Where is cosine x equals 0 on the interval 0 to 2 pi? Back to trig class, right? Some of you better know this, because I think I remember having you in trig class. Huh? Where is cosine x equals 0? Between 0 and 2 pi. At half a pi. So this will be 0 at x equal pi halves. And at 3 halves pi. That's sounding better now. Okay? It's 0 plenty of other places, but that's the only two places it's 0 on that interval. So let's go to the other one over here. What would you do here? this equation? Subtract 1 from both sides. Sounds like a good thing to do, and that would give you 2 sine x is equal to -1. And then what? Divide by 2, and that gives you sine x is equal to -1/2. Now, where on the interval from 0 to 2 pi is sine x equal to -1/2? Second? At pi 6, it's 1/2. Okay, let me ask this question. Where is sine negative? Quadrants 3 and 4, exactly. Okay? But the 1/2 is important because that's your reference angle. Where is the reference angle of pi 6 in the third quadrant? 7 pi 6. 1/6 more than pi. Okay? So this would be x equals 7 pi 6. And 11 pi 6. 1 pi 6 short of 2 pi. And that's exactly it. So now we have 4 candidates here where the first derivative is equal to 0. And then what else do we have? The endpoints. Okay? So we got 6 things to evaluate. Okay? But we go back to the function to evaluate. So, which one you want to start with? I really don't care too much. 0, okay? So, what is f of 0? It's 2 times the sine of 0, I can't write, minus cosine of twice 0, which is still 0, okay? And what will that be? Okay, sine of 0 is 0, so that first term is going to be 0. But what's cosine of 0? 1, but you got a minus, so that's going to be -1. So here we have a -1, okay? Got it? Which one you want to do next? Pi halves, you said? Okay, so let's do f of pi halves. Okay, go back to the function. That's 2 times the sine of pi halves minus the cosine of 2 times pi halves is, say again? 2 times pi halves. That'd be 2 halves over 2, which is pi. Okay, I like the sound of that. Okay, I like pi. Okay. Oh, by the way, Happy Pi Day. This is 3/14, isn't it? March the 14th. You know what else happened on March 14th? Albert Einstein's birthday. Believe it or not. Yeah. And 2 years ago, it was a very special Pi Day. Because it was 31416. Okay. Very good. Okay. We were much more precise that year than we are this year. Okay. We just rounded the second decimal place, then we rounded to the fourth. Okay. All right. Enough of that. So, what is sine of pi halves? Oh boy, back to tree class. Say again? Sine of pi halves. Okay, let's go to the unit circle. Here's sine of 0. Here's sine of pi halves. 1! Of course it is, okay? So that would be 2 times 1 is 2. What's cosine of pi? Okay, cosine of pi is -1, because cosine, remember, starts up here, goes down to 0 at pi halves, down to -1 at pi. Okay? But it's minus the minus 1, so that would be plus 1, so that would be 3. Okay? All right, so we could have a minimum and a maximum here. We'll see. Which one do you want to consider next? I really don't care too much, but you tell me. 3/2 pi, so f of 3 pi over 2 will be twice the sine of 3/2 pi minus the cosine of 2 times 3/2 pi would be what? 2 times 3/2 pi. 2 pi. 3 pi, right? It's 2 times 3 pi over 2. 3 pi. Cosine of 3 pi. Okay? And what's the sine of 3/2 pi? Oh, we need to send some people back to tree class. Huh? -1. So that'll be 2 times -1 will be a -2 minus, and here's Elijah. We're slowly making more. And by the way, a couple of people have come in since I asked the question before. Everybody got a copy of the second test, right? I guess another question that goes with that is everybody turned in the first test, okay? And maybe another question that goes with that is how many of you have done your paper? Some of you have, but some of you haven't. You don't have to have that done yet, but I wouldn't put it off super long, okay? Never have more time to do it than you do right now. Okay, so let's get back. Cosine of 3 pi. What is cosine of 3 pi? -1, because it starts at 1, goes to -1 at pi, and then its period is every 2 pi, so 2 pi later, back at -1, but you have a negative times a negative, which is +1, so this comes out being -1, okay? So we have a tie now for a potential minimum, okay? 0 is -1, and 3/2 pi is -1, okay? What you want to do next? Next? 7 pi over 2. So f of 7 pi over 6. I'm sorry, I said it wrong. And that's equal to 2 times the sine of 6 pi minus the cosine of 2 times 6 pi. What would that be? Two times 6. 7/3 pi. 7 pi over 3. Okay. This one's going to take maybe a little more head scratching here. Okay. First, what is sine of 6 pi? Negative. What? -1/2 times 2 is? Okay, send back to fractions, okay?
You said -1?
-1, exactly. 2 times -1/2 is -1. All right, now more head scratching here. Cosine of 7/3 pi. 7/3 pi is a pretty big number. So what I want to do is subtract 2 pi from that, right? How many thirds pi is 2 pi? many thirds is 2? 6 thirds, right? So we subtract 6 thirds pi, which is 2 pi, from 7 thirds pi, and what do you have? Pi thirds, okay. Now, what is cosine of pi thirds? See why we did that. We're using the period distance. Pi thirds is? You all know what I'm talking about, huh? If this is 0, pi halves, pi thirds is right there. So in the first quadrant, huh? 0? 0 is only going to, sine of 0 is 0, and cosine of pi halves is 0. Neither one of them is 0 in between that. What's cosine is 1/2. Is that what you said? Yes, 1/2. And you got minus a 1/2, right? So minus 1 minus 1/2 is minus 3/2. Okay. Looks like we have a new minimum, doesn't it? So far. Because that is less than either of those two up there. So these two are out. Too bad. 0's out and 3/2 pi is out. Still have a potential maximum, still have a potential minimum. What you want to consider next? Okay, we can do 2 pi. So f of 2 pi would be 2 times the sine of 2 pi minus the cosine of 2 times 2 pi is 4 pi. Okay. Now, what's the sine of 2 pi? Okay. Multiple choice for me, huh? All right. I like multiple choice tests. Okay. You want to help them out? Okay. Okay, again, multiple choice for me. All right.
I think it's 0.
It is 0 because sine of 0 is 0 and sine of 2 pi is 0. Okay, so that would be a 0. Okay, and what's cosine of 4 pi? Yes, so we have minus 1. Here we have another minus 1, and we already found out those are out of the picture. Okay, because we got something less, we got something greater. We're missing 1, folks. We had 6 to consider. 1, 2, 3, 4, 5, 6. 11, 6 pi. I'm going to have to do that up here. F of 11, 6 pi would be 2 times the sine of 11 pi over 6 minus cosine, and what's 2 times 11 6 pi? 11 pi over 3. Okay. What is sine of 11 6 pi? Negative 1/2. And 2 times that would be? Negative 1. Okay? Minus. And what's cosine of 11 pi thirds? Yeah. Well, that's a pretty big number. So what do we typically do with that? Subtract 2 pi from it, because that's 1 period. That gets you right back where you were. How many thirds pi is 2 pi? Already had it once. 6 thirds pi. Subtract that from 11 thirds pi, and what do you have? 5 thirds pi. Exactly. And what is the cosine of 5 thirds pi? Where are we with 5/3 pi? Okay. You're 1/3 pi away from 6/3 pi, right? 1/3 pi. Fourth quadrant. And what is cosine in the fourth quadrant? Sine. S-I-G-N. Positive in the fourth quadrant. So, and what would be the value of, what's your reference angle there? Pi thirds. What's cosine of pi thirds? One half. Okay. So it would be 1/2, so it's minus a 1/2. Okay? Well, that gives you minus 3/2, which is tied for this one. So 7/6 pi and 11/6 pi. I'm surprised at that, but I guess it's true, are both negative 3/2. So we have a tie for the minimum, and we have an absolute maximum, pi halves. Let's see what the book got. You can see the maximum up there at pi halves 3. That's exactly what we got. And then we have a tie for the minimum at 7/2, negative 3/2, 7/6 pi, negative 3/2, and 11/6 pi, negative 3/2. The others are intermediate. A -1, -1, and -1. Okay. See how that works? Had 4 critical values. One of them produced a maximum, 2 of them produced tie for minimum. And the endpoints and the one other critical point gave you something intermediate in between. All right. I feel like a dentist now pulling teeth, so let's move on. Concept check here is basically read those questions, see if you understand what they're asking, okay? Then the homework exercises, do any of the odds 7 through 11. All 3 of those are at calcchat.com, 7's at calcview. Do either 13 or 15, they're both at calcchat. Do any of the odds 17 to 21, all 3 of those are at calcchat, 17's at calcview. Then do any of the odds 23 to 39. There's a whole passel of those, maybe a passel and a half. All those are at calcchat, only 25's at calcview. Do either 41 or 43 or both. They're both at calcchat, 41's at calcview. Do either 45 or 47. They're both at calcchat. Neither of them are at calcview. Do 49, it's at calcchat. Do 51, it's at calcchat. Do 53, it's at calcchat. And then there's a writing one that you have there. If you can do it or not, it's up to you. 55. Then in exploring concepts, either 57 would be pretty good to take a look at that. It has an A and a B part. And then 59 is considering critical numbers again. Okay? Then you have some one applied problem, 61. You can certainly do that if you'd like. Oh, I'm sorry, there's 2 of them, 61 or 63. Okay? Well, actually some more. No, not odds. Then some true false, 65 or 67. Don't expect many of those on the test, but you can look at them. 69 is something you can think about, and there's a Putnam challenge there, which may be sort of like some of the stuff you do on math team. I don't know if you get that involved or not. All right, let's clear that out of the way, and we'll start 3.2. Okay, back up. 3.2, again, applications of differentiation. Now we're going to look at a couple more. First, we're going to look at 3.2 is dealing with Rolle's theorem and the mean value theorem. These are both things that come out of differentiation, applications of differentiation. The objectives is understand and use Rolle's theorem, understand and use the mean value theorem. They're pretty straightforward. So what in the world is Rolle's theorem? Okay? Now, The extreme value theorem states that a continuous function on a closed interval, a to b, must have both a minimum and a maximum somewhere on that interval. Okay, we know where to look. Take a first derivative, anywhere that's 0, that's a candidate, called a critical point. Anywhere it's non-defined, that's a candidate, it's called the critical point. And we also look at the endpoints. Okay? Both of those values could occur at your endpoints. You may not have one at a critical point. Rolle's theorem. Now, if you are that interested in Rolle's theorem, you could use that as your paper topic. Or if you're just interested in who came up with it, Michelle Rolles, probably a male Michelle, female would have an LLE on the end. Rolle lived from 1652 to 1719. What was going on in France then? Any ideas?
Is it King Henry VIII?
Okay, that's in England. Yeah, he was in England. But yeah, this was probably maybe one of the Louis. They had a whole bunch of Louis right in the road. So it could have been them. It was back in the monarchy, before the French Revolution. The French Revolution was 1791 or something like that. So this is back in the sort of the heyday of the French monarchy. And, you know, they were pretty much, Paris and France were centers of learning then. Pretty big times there. It gives conditions that guarantee the existence of an extreme value in the interior of a closed interval, not counting the endpoints. Okay? So here's Rolle's theorem. Let f be continuous on a closed interval a to b. Still got a closed interval. Differentiable on the open interval a to b. So it has to be differentiable there. Okay? Now what does that mean? It has to be both continuous and smooth to be differentiable. Okay? What that leaves out are cusps, angles, those kinds of things. Absolute value could not include, you know, point there. You can't include anything that doesn't have a derivative. Okay? Now, if f of a, this endpoint, and f of b are the same, so wherever that is, they're the same at the endpoints. Okay? Then there's at least one number c in that open interval a to b such that f prime is equal, f prime of that number c is equal to 0. So that means you will have some place where your first derivative is 0, so you do have a candidate for a maximum in inside that interval. There will be at least one. Okay? So f has to be continuous and differentiable. Okay?
Does say that they're the same height? F between
F of A and F of B, the y values are the same. Yeah. Okay. So from Rolle's theorem, you can see that a function is continuous on AB and differentiable on the open interval AB. And if f of A is equal to f of B, there has to be at least one x value between A and B where the graph has a horizontal tangent. So it's going to either be a relative maximum or relative minimum. Okay? So let's say that f of A and f of B was this value d down here. Okay? The function's doing something in between. Now, of course, if the function was a constant function there, every point is the same value. Okay? That's not very interesting, but it could happen. F of x is equal to d. Okay? Endpoints are the same and every point in between is the same. But if it's doing anything else, there's going to be at least one place, because it's got to be continuous and differentiable, where if it's going up, it's going to have to turn down, so it's going to have a horizontal. If it's going down, it's got to go back up. It's got to have a horizontal tangent somewhere. It could have several of them. Okay? Then it would have several possibilities. Okay? So, that's basically what Rolle's theorem is saying. when the differentiability requirement is dropped from Rolle's theorem, f will still have a critical value or a critical number on A to B. See, here is a cusp. That's not differentiable. Okay? Derivative is not defined at C. It's infinite. Or even if it wasn't infinite, it has a different value from the left as it did from the right. This is a very positive derivative coming from the left, but a very negative derivative coming from the right. So it's not differentiable at that point C. Okay? So if we drop that one, we could have this. It's still going to have a critical number in AB, but it may not yield a horizontal tangent. This would be where the limit doesn't exist, so therefore the derivative doesn't exist. Such a case is shown here. Now, remember, we're not dropping the continuity, we're only dropping the differentiability. So, again, if it's going up and coming down, it's going to have a maximum. If it's going down, it's got to come back up, okay? So, there's going to be a relative minimum there. And it could do that several times in between. Just wouldn't have a first derivative of 0, it would have a first derivative of undefined, or, okay? So, here is example 1, illustrating Rolle's theorem. Okay? This is on top of page 175. Okay. Find the two x-intercepts of this function, x squared minus 3x plus 2. How do we find x-intercepts? What is an x-intercept? So, factor it, exactly. Because the x-intercept is where y is equal to 0, right? If this is a function, that's a parabola. No, it's a parabola, however it's going there, either like this or like that. And if it has an x-intercept, that's where y is equal to 0. Because the two places it crosses the x-axis, y is 0. So you set y, which is f of x, equal to 0, and factor it. So the first thing we do is set this equal to 0, and see if we can factor. Can we factor that? Okay, that would factor as x times x. That's the only way you can factor x squared. And then you look at the sign of the last term, that's positive. That means these two signs have to be the same, either positive or negative. Look at the middle sign, it's negative, so they both have to be negative, right? And then what two numbers multiply to be 2 and add to be 3? 1 and 2. Okay, buckle my shoe. Okay, so what are your two x-intercepts? Yeah, x equal 1, x equal 2. So guess what? At those 2 points, you have the same y value. 0, right? The x-intercepts are both 0. So somewhere in between there, you have a relative maximum min. Does anyone want to make a guess of whether it's a maximum or minimum? What kind of function is that? Second, it will be a minimum. Why? Because quadratic functions open up if a is positive, meaning the coefficient of the x squared term, and that's positive, so it's opening up, so that has to be a minimum. Very good, okay? So, now it says show that we know it's got to be equal 0 somewhere in between those two intercepts. So, how do we figure out what F prime is? Yeah, take a derivative, and what does that? 2x, second? Really? Minus 3, okay. And set that equal to 0, and what does that give us? X equals 3 over 2. Add 3 to both sides. 2x equals 3. Divide by 2, and you get x equals 3/2. And sure enough, that's smack dab in between 1 and 2. And we knew it had to be because of our symmetry of a parabola. Okay? Absolutely. It had to be right smack in between. Okay? So F prime does have a horizontal tangent place where the derivative is 0, and it happens to be directly in between those 3/2. Okay? So that makes you feel warm and fuzzy, doesn't it? So it's exactly what you would expect. And we know that happens to be a minimum. How do we know that? Well, because A is positive, but what you can do is plug in this X and see what you get. If it's a positive number, it must be a max. If it's a negative number, it must be a min. What do you have? 3/2 squared is what? 3/2 squared is 3/2 squared. 9/4 minus 3 times 3/2 is 3 times 3/2 is 9/2. So you have a 9/4 minus 9/2. Well, if you wrote that 9/2/4, that'd be 18/4. So it'd be 9/4 minus 18/4 would be minus 9/4, right? Right? And then add 2 to it. Well, what's 9/4? It's a negative number, and it's greater than 2 or less than 2? 9/4. Yeah, 9/4 is 2 and 1/4. So therefore, it's a negative 2 and 1/4 plus 2, negative 1/4. Yep, minimum, just like you said. It was. Okay. They didn't carry on like that, but I did. Okay. All right. Let's clear this out of the way so we can see how they worked it. Note the F is differentiable. It's a polynomial. Polynomial functions are always two things: smooth and continuous. Always. Sines and cosines, always smooth and continuous. Okay? Not all functions are smooth and continuous, but those are. Okay, so F is differentiable on the entire real number line. So setting F equals 0 produces exactly that. We factor that just like they did, and you get either x equal 1 or 2. So that means you have to have a relative max or min in between 1 and 2. So since f of 1 equal f of 2 equals 0, Rolle's theorem, you know there has to be at least one value c in between 1 and 2 such that f prime of c is 0. Well, just take the derivative of f, you get 2x minus 3, and then set that equal to 0, and that comes out being x equal 3/2. I'm sorry, I'm running out of energy. I did this yesterday about this time too. Still having fatigue. Maybe it's just old age. I don't know. But, well, and then to daylight saving time. And then to the last 2 nights I've received late night phone calls that just went on and on and on. My brother, night before last, and then last night, our cleaning lady, and she's a talker. So my wife's out of town, so I could not answer the phone. So anyway, running low on juice here. Note that this x value lies in the open interval 1 to 2, shown here, and exactly in between. Has to be because of the symmetry of the parabola. The horizontal tangent is down here, and that is the negative value at negative 1/4. We didn't do that. I mean, the book did, but we did. Okay. Lies between the two x-intercepts. Okay. Can you say the same thing about y-intercepts? If a function has 2 y-intercepts, it can't be a function. Y-intercepts is vertical line. Yeah, no. Okay. Trick question. All right, before we move to mean value theorem, let's back off and do example 2. They do the easy one for us on the slide set, but then this is a little more involved. F of x equal x to the 4th minus 2x squared. Okay? It says first find all values c on the interval -2 to 2 such that f prime of c is equal to 0. All the values on that interval, -2 to 2, such that f prime of c is equal to 0. So what do we better do first? Take a derivative. Okay, let's do it. F prime of x is equal to 4x cubed minus 4x. Okay? And we're going to do what? Set it equal to 0. And what do we get there? Okay, yeah, we could divide by 4. That is legal. Okay? And that's going to wipe out our 4's here, and 0 stays 0. Okay? So that gives us x cubed minus x equal 0. Now what do we do? Say again? I'd rather not. I like having a 0 over there because of the F word. Huh? I wouldn't want to do that either. Factor, yes. So this is a higher order equation equals 0. Don't mess with that 0. Okay? Factor out an x. And what does that leave us with? X squared minus 1 equals 0. Can we do any more factoring? Oh, we're through with Math 100. Do I have to ever factor again? Wrong. X plus 1 times x minus 1. And that product of 3 factors is equal to 0. What does that tell you? Either x equal what? 0, or x equal -1, or x equal 1. 3 values c such that the first derivative is 0. We just did it. That's going to be x equals 0, x equal 1, x equal -1. So on that interval, there are 3 places where you will have a relative maximum or minimum. Okay? And they show you the graph in the text. Do all of you have your book or an e-book or something that you can look at? Okay. All right. There is something they call here at the bottom of the page a technology pitfall. A graphing utility can be used to indicate whether the points on the graph in examples 1 and 2 are relative maximum or minimum functions. You can use the graphing utility, however, you should keep in mind that it can give misleading pictures of graphs. For example, a graphing utility to graph f of x is equal to 1 minus x minus 1 squared minus 1 over 1,000 times x minus 1 to the 1/7 power plus 1. With most viewing windows, it appears that the function has a maximum of 1 at x equal 1, shown in this figure in the text. By evaluating the function at x equal 1, though, you can see that f of 1 is equal to 0, not 1. Okay? Now that's pretty interesting. When you plug in x equal 1, see the first one, let me write this out. I don't know. Is it worth taking the time to do? Okay. Well, no, it isn't, is it? We just ran out of time, didn't we? No, we didn't. We got 4 more minutes. Sorry. Let's see if we can do it. Here's your f of x is equal to 1 minus x minus 1 squared minus 1 over 1,000 times x minus 1 to the 1/7 power. What's that? You did it? And what do you get? Yes, it is 0, and here's why. 1's still 1. This right here, 1 minus 1 is 0 squared, is going to be 0. We've got 1 minus 1 over, now x minus 1 is still 0, right? 0 to the 1/7 power is 0. 1,000 times 0 is 0. Plus 1 is 1. So you have 1 minus 1 over 1 is 1. So 1 minus 1 is 0. Sure enough, that is. Why did the graphing calculator show you have a relative maximum there? I think it has something to do with that 1,000. Okay? What's that? Yeah, and probably the x minus 1 to the 1/7 also. So let's see if they tell us anymore. Is it on the next page? No, it isn't. That's bad. They just leave us hanging there. To determine the behavior of this function near x equal 1, you need to examine the graph analytically to get a complete picture. Okay? Now, I don't know exactly what they mean by that. Usually that means you can do it pen and paper, pencil and paper or whatever. But I would be more tempted to try to expand the graph, but that may not work. Okay. Certainly, if you took a derivative of that, you're going to have a mess, a really bad mess. But that may give you some more insight into the situation here. But to me, it's not worth taking the next 3 minutes to do. Okay. Now we got 1 minute. So, do we have time for mean value theorem? I don't think so. So I guess what we'll do is just go to homework exercises. I think you can do either 3 or 5. They're both at calcchat.com. And you can do either 7 or 9. They're both at calcchat, but 9's also at calcview. And you can do any of the odds 11 through 23. They're both at calcchat, all at calcchat. 13's at calcview. You can do either 25 or 27. They're both at calcchat. Neither are at calcview. And then you can do number 29 if you like. That's at calcchat. Okay. We will pick up with mean value theorem next time on page 176. Okay. Now this section has the chapter has lots and lots of sections. However, some of them are pretty short, like this one. So we should be getting through them fairly expeditiously. Okay? We'll see. Good deal. All right. Have a good weekend.